Welcome back to the second hour. I'm going to start discussing something that was asked on the Zoom chat to clarify with the exercises. So as I said, because of space repetition, we are offsetting by 1 week. So this week, tonight, you're going to have the Boolean retrieval exercises that corresponds to the lecture of last week. It means that the exercises will be released today. The notebook, the Jupyter notebook will be released today. And you're going to have the exercise session on it today for the hints. And then you'll have 1 week in order to work on this. And then the solutions will be next week. And then next week, you will discuss this week of material, right? The Jupyter notebook, from what I understand from the TA team, so we have this Jupyter hub, right, that is hosted by the department. You will get a copy of the notebook every time in a shared folder. You need to copy it over to your own folder every time before you edit it, right? So this is very important. You need to make that copy every time, but you'll get more precise instructions when the time comes, right? But this is going to be tonight. I encourage you to solve these exercises, even though it's not graded, because that way you can programmatically build a standard inverted index, and then you make sure that you really understand the tiniest details of how it is built. But you won't have to worry about what we are talking about today, because the tokenization comes from for free in the exercise. Was there any open question? It's ungraded, right? Yet, and we announced the 3 weeks where it's going to be graded. Did it answer your question on Zoom? Yes, wonderful. Thank you. All right, so we'll just continue. What's funny is that tokenize nowadays means something else in the concepts of crypto. But anyway, it existed before as a word. So tokenizing just means by space like this. But I wanted to come back to this example of last week in terms of the words that we use. So I already told you about the word term and the word token, right? So token is what you get when you have done this separation by space, right? So our is a token. It's a grouped sequence of characters. With all the words of warnings I told you about languages, that tokenizing is not easy, is not that easy in all languages and for various reasons. But basically, the token is really in the original documents, some sequence of characters that you want later to convert to a term for the inverted index, right? So the token is a raw form of a term, if you want. Now there's a new word here that we'll discuss today, which is called the type. This has to do with what happens when you conjugate verbs, when you have like computer, computers, am, is, are. These are all conjugations of to be and so on. So this together is called the type. This is the term that experts in information retrieval use. So a type can be seen as an equivalence class over tokens, right? It's all the tokens that are kind of the same thing, right? It can be the plural form and singular form of the same thing, can be the conjugation of a verb. In German, it can be the same word like Präsident, Präsidenten, like all the declinations that you can imagine. Okay, that's called the type. And then we take the types as the terms in the inverted index, as we will see in some cases, right? But I'll come back to that. All right, so type. This is the new word that I'm introducing here. So you will not be surprised if you see it. Then there are words that are called stop words. The stop words are all these words in English that are all over the place with super high frequency. In fact, they are so frequent that almost any web page or any book is going to have them. For example, and, are, as, at, be, by, for, from. So these are so often encountered that if you look at the postings list that would correspond to these stop words, would it be small or big? It would be big, right? It would have almost all the documents in there. So you can imagine the space that it's going to take for the stop words. Is there any information in the stop words? You could argue that not really, right? It's everywhere. So what does it bring us to actually know that the stop word is everywhere, right? For this reason, the stop words are just thrown away typically, or were, I'll come back to the historical things, but they used to be thrown away. You just take the top 30 words. So this is the Reuters list. It used to be a larger list before, so 200, 300 words, also because computer resources were more limited than today. But what's interesting is that this is kind of disappearing. Nowadays, we don't bother with stop words anymore. There are several reasons for that. For example, you might want in some circumstances still accept, like when you're a search engine. Let me give you an example. You search for C in a search engine. Maybe 50 years ago, nobody would have done that except looking for the letter C, right? But nobody would do that. But today, C can mean the language C. So indexing the web has become more complicated. And I think this is part of what led to the fact that we don't eliminate stop words anymore. Another aspect is that we are no longer constrained by computer resources as we were before. So we are doing it just because we can. In a way. So this is why there is this trend of stop words disappearing. But it's still interesting to know, and you have to know, if I tell you stop word, then you have to know that this is what it means, right? It's you take the very highly frequent words and you throw them away and don't even include them in the index. Okay. Now I'm coming back to the types. The types, this is what I said here. I said it's an equivalence class. So if you look at this, probably that makes sense now, right? So if you see USA with points or without points, window, Windows, Windows, today. So 2-day is how it used to be spelled in the 19th century. This is an example of where it actually lost the dash and now it's a single word. Tomorrow also used to be in 2 words. Now Zurich in Swiss German, Zurich, the English version, you could put all of that in the same bag. But it sounds easy, right? You can just eliminate the difference and just standardize things, right? You remove the dots in USA, you remove the dash in today and so on. So you could try this in this way. But it's challenging because, for example, Windows here could mean the operating system. You might actually not mean a window like this. So for this reason, there is also an asymmetric way of doing things. You know, who knows what an equivalence relation is, equivalence class? I think you learned that in discrete math, right? You remember it's symmetric, an equivalence relation. If X is related to Y, then Y is related to X. So this is why I mean here it's asymmetric. It's no longer an equivalence relation. It's called actually an expansion. So here, Windows would be expanded to the same because you could consider it's capital W, it's probably the operating system. Windows would be expanded to all 3, window with a small w to just window and Windows. This is called an expansion. This is different than types and equivalence classes. Just need to be aware to separate that in your mind. This is another approach. So if we use expansion rather than equivalence classes and types, then we can do it in 2 different ways. One way to do it is to expand the index. So let's take lift and elevator, for example. So imagine the original documents here. Documents 1 and 5 contain lift. Documents 1, 4, 6 contains elevator. Then you can expand the standard inverted index, that's post-processing, that's done later, by merging the postings list, doing the union for both. So if somebody looks for lift, they will also find documents 4 and 6, even though it does not actually contain lift, it contains elevator. But you see why we want to do that, right? Because somebody looking for a lift might be interested also in documents that contain elevator. So here it has to do with British English versus American English, right? So you can do it in this way. And when you query for lift, then you will get 1, 4, 5, 6. So this is one way. The other way is the other way around. You expand the query, not the index. So here you have lift, which would transform to lift or elevator. And then you compute the union also of the standard inverted index, but you do it lazily. You only do it at query time, right? So here, you surely understand that this takes more space, right? Because you need to actually materialize an index with more postings. This takes more space, but it's faster. Here, it takes less space, but it's slower because dynamically at runtime, you need to actually do more work, right? More space, more time. For whom is that clear? All right, and I don't need to ask the question. All right. Something else is with the accents, which is part of the, you could consider it as part of the equivalence classes, but it's not the same in all languages. There are languages in which you can just kind of drop the accent and it doesn't really matter, you can still understand it. But there are languages in which the accents actually are not just removed. For example, in German or in Swiss, well, Swiss German might be a bit different, but in German, High German, U umlaut, A umlaut, O umlaut, you add an E, right? In order to if you don't have the umlaut available, right? So Zurich would be written in this way with an E that basically is equivalent to the umlaut, right? In Swiss German, it's not so easy because UE actually exists, like we got gut, right? So UE doesn't actually mean good, except in Wallis, where they actually say gut, but it doesn't have the same semantics as it would have in High German. But just to say that here too, you need to be careful with these things. In French, for example, the circumflex, so the hat, is technically replaced with an S. Right. If you omit it, then you should put an S after that. But I don't think it's something people would do as spontaneously as the E in German. I think the E in German, a lot of people do it. In French, probably not everybody even knows about that. All right. Then something you can do is also lowercasing. You just put everything to lowercase and you remove the punctuation. So this is what you end up with. So these are all strategies that you can have, right? But again, you have the problem that you might have proper nouns, like Apple with a capital A might be the brand and not the same as apples, right? And then you can see what makes it worse is that it could be the beginning of a sentence, in which case you do have this uppercase A right here. So then this is when machine learning actually starts making sense to actually tell the difference, right? So as I told you, we are not doing machine learning here. You have introduction to machine learning. I think, by the way, there's 1,300 people in there, very popular lecture. So this is why we are not doing any of this here. It's complementary, and you can use the techniques from this other class if you learn them. All right. Yet another thing you can do is called stemming. What is stemming? I'm going to explain to you in contrast to something called lemmatization. Lemmatization, we've already discussed it, in fact. It's when you conjugate verbs, right? And you understand that is, am, be, are, this is all the same verb. This is to be, right? So this would be called lemmatization because you have an actual understanding of the language and of the grammar, right? So you are aware of the meaning and of the fact that it is the same verb for grammatical reasons. Stemming is totally different. Stemming basically doesn't even understand anything. It's like ChatGPT. It doesn't understand anything. It just follows a set of mechanical rules blindly and just applies modifications to the words by chopping letters at the end, right? So this is what it does. It's, of course, not going to work in the same way in every language, but it turns out that in English, it was widely researched, and there are a couple of stemmers out there. So these are the sort of rules that you can have. It's really very mechanical, right? So you have these rules that say if it finishes with, I don't know, ently, then you just put ent, usly, us. So these are the transformation rules, and you apply them repeatedly, and then you arrive to something called the stem. Right, and then the stem gives you the type. That's the equivalence class that you're looking for. All of the tokens after stemming that leads to the same stem are put in the same equivalence class, and they are all together in the standard inverted index. Just so you know, there's plenty of stemmers. The most famous one is the Porter stemmer. The Porter stemmer, in some classes, you can even program it as an exercise. I don't think we will do it in this course, but you can actually implement it very easily. So these are three stemmers. So the original text is in bold on the top. This is what you have in the book. If you apply the Porter stemmer, then you get this: such an analysis can reveal feature, blah, blah, blah. Then the Lovins stemmer and the Pice stemmer. So you see they just lead to different results. What difference does it make? Well, it's just the end feeling of the system at the end, right? That the words might not end in exactly the same equivalence classes, so they work in all their own ways. How would you be able to tell the quality? Well, it's with the evaluation that I told you about last week: precision, recall, and all of these metrics that we're going to look at, right? So you have several alternatives, several different technologies contributed by different people. Then you can just go ahead and use them and see the results. What's very important is that these stemmers here are only for English. It will not work in other languages, because you saw, for example, the rules here. The isation, eyes, this is really made for English. Asian, usly, us, and so on. This is English specific. If you want to do it in other languages, I don't know much if people actually did it in other languages, but it would be different. It wouldn't be the Porter or Lovins or Pace stemmers. Okay, who is with me? Okay, so the most important part is that these stemmers are mechanical. It's just a bunch of rules, a few hundred rules. You just follow them mechanically and apply them, and then you get this. And that gives you the actual terms that you put in the inverted index like this. And of course, you apply the stemming to the query as well if you want to find the actual terms in the index. Okay, so you see it's an extra layer on top of the standard inverted index that does that. Lemmatization, I put the slide, but we've already done it because I told you that's the conjugation, right? So this is the idea that you're actually doing natural language processing or natural language understanding, as it's called nowadays. There are lectures at ETH, I think that bear the same name, like natural language understanding. So anybody who wants to learn more about human languages and understanding languages, translating across languages, you can take this lecture. It's a very, very nice topic. And as part of this, of the natural language understanding, there is this pyramid that is commonly shown, which is the way that when you translate from a language to another, you can do that at different levels. You can try a direct translation. You can do on the syntactic level, on the semantic level. And this is kind of an idealization. I don't even know if it exists or if it's been done yet, but that would be an ideal universal language that contains everything. And then if you want to translate, you just bring it to that language and then translate it back to another language, right? That's called interlingua, or yeah. And that's called the Vauquois triangle, this thing here. Okay. But we are not going to do translation in this lecture, right? This is really specific to what you learn in natural language understanding courses. So part of lemmatization is also to consider what's called morphological analysis. It's a scary word that just means that, for example, computer, compute, computes, computed, computation, computing, you just kind of put them together when you look these words up in an information retrieval system. In fact, if you try it with Google or Bing or DuckDuckGo, you will notice that kind of behavior, that it's actually automatically also searching for words that are morphologically close. Okay, now, since we talked about stemming and lemmatization, comes the question, should we use lemmatization or should we use stemming? And the answer, for just as usual in computer science, is it depends on the use case, right? It's the same. I mean, there are things that probably are never-ending debates like VI versus Emacs or Linux versus Mac, or I don't know, but in many cases, this is actually factually debatable based on the use case. In English, we know that stemming is very powerful. If you have a language like, so what did I put here? Spanish, German, French, Hindi, here morphological analysis works better. So here you want to use lemmatization rather than stemming. It's going to be much higher quality when you actually look things up, all right? Okay, so I'm done with the languages and lemmatization, stemming, and so on. Again, if I want to summarize what I have said, I just want to show you it's not easy at all. And because of that, we have to add more bells and whistles to the standard inverted index in the form of equivalence classes by putting similar words together in the same term for the inverted index, or expansion, which is an asymmetric version as opposed to equivalence classes, right? Who is with me before I talk about skipped lists? Okay, this is completely different. It's a context switch, so now you can put aside what we've done until now. I'm coming back now to something algorithmic, so that should be almost restful for you. We're coming back to how we traverse these postings lists as we saw last time. So we built, for example, here the standard inverted index, and we saw how to intersect when you have an AND in the Boolean query language. We saw this intersection algorithm of two linked lists. Now, here is an example that we are going to intersect on. I have two terms, list A and list B. I don't know what terms these were, but these are just two terms and they're posting lists. So we do the intersection. Okay, 1 and 1, that's the same. Then we advance here both. Then 2 is not the same as 3, so we increase only the pointer of 2. Then we have 3 on both sides. Now we compare 10 and 4, so it's different. So we move the pointer that has the smaller one, which is 4. 10 and 5 is different, so we move the smaller number pointer. 6 and 10 is different, so we move up the pointer to 6. Now we have 7 and 10, it's different, so we move up the pointer to 7. Now we have 8 and 10, it's different, so we move up the pointer to 8. Now we have 9 and 10, it's different, so we move up the pointer to 9. Now we have 10 and 10, bingo. It's the same. Now we move both of them. 11 and 12 not the same. 12, 12 matches, and then 14, and we are done. What happened here? You notice something inefficient? Yes? Yeah, we had a lot here, you see. We had repeated comparisons here, but they all failed. Why? It's because here we have a small postings list and there is a big interval here, but here there's a lot of them. Maybe that looks even like a stop word here. 1, 2, 3, 4, 5, 6. That's a stop word, right? But assume I have this stop word and then I have this huge interval there. Can we do better? The answer is yes, we can absolutely do better. And the way we do better is with a magical pointer. Imagine we have this magical pointer there from that starts on the 4 that tells us that if you follow that magical pointer, you reach 10. Can we use that magical pointer? Yes, absolutely. Because what do we know thanks to this pointer? We know that anything before the destination of the pointer is not going to compare successfully with 10. So we can just directly jump there, you see, with this magical pointer. And then we actually gain time. But of course, it only works if we have this magical pointer. If we don't have it, then there's no way we can do that. And of course, if you want to have the pointer, you actually have to build it and to construct it. So in practice, you can have multiple pointers in the postings lists, the ones with high frequency counts. So here, for example, we can directly jump from 1 to 4, and then to 4 to 7, and then from 7 to 10. The details of the algorithm to know when to jump pointers is in the book. There's even pseudocode written in the form of an algorithm that I strongly recommend you look at to make sure you are aware. In particular, you need to understand how many comparisons you make and so on, following that algorithm. Now, let me tell you. So, or maybe you can guess, what is the size of the jumps that you think we could have? It's the square root. So typically here we have, if we have 16, you say 4 by 4. So you basically take the square roots. If it's too short, then that's going to be too much overhead to build, and it's going to be very useful. It's not very useful. But if it's too long, then you barely use it, because maybe you never get a chance to actually make any use of it. So you just take the square root of the size of the posting lists, 4 by 4, 5 times 5, 6 times 6, roughly, right? So this is what you do in practice, right? The square roots. Okay, who understands skip pointers? All right, so again, you need to actually actively program them and build them if you want to use them, and typically you put them in the square roots, every square root postings. Okay, and one last thing that I want to tell you about is phrase search. When you type something in Google, it's not actually a Boolean query. Well, it can be interpreted as a Boolean query, but it's also going to interpret as a phrase. ETH Zurich, you probably want them next to each other. In fact, you can force that with quotes. This is called a phrase search. This is not in the Boolean language. It's an extension of the language. And typically, you do it with quotes. All right. Now, how do we execute a phrase search with the standard inverted index? The answer is we can't. We can't. Why? Yes? Exactly. Yeah, we don't have the position of the world. All we know is that document 1 contains ETH, document 1 contains Zurich, but you have absolutely no idea. They might be next to each other, or maybe ETH is at the beginning and Zurich is at the end. In fact, it could be document 1 could be the web page of an Ethereum cryptocurrency website that is located in Zurich, for all you know, right? But what you want is ETH Zurich, the actual university, right? So we need something else, because it doesn't work just with standard inverted indices. So there are 2 ways that you can actually do that to extend the system. The first way is with byword or keyword indices, and the other way is with positional indices. So what does that mean? It's very intuitive, you will see. Byword indices means that instead of indexing term by term, you have a sliding window of k terms, 2 in that case. So here you have LPTH, ETH Zurich, Zurich 2 flexibly, flexibly react, just move the window. So you see you have all pairs, and then you still have these postings IDs of the documents in exactly the same way. So now you might not have the full order of the documents, but at least you have the neighbor terms, right? You know that, for example, the documents in the first posting list here, they contain help ETH next to each other, right? So now, how do you run a query? So ETH Zurich, it's only 2 words, so this one is easy. You just look up for exactly that pair in the inverted index. It's no longer the standard index, right? It's a by word inverted index. And then you see here, all of these documents here contain ETH Zurich. So now we can answer this query. However, what about this query? It's made of 6 words. Well, we could decompose that into with an end of help ETH and ETH Zurich and Zurich 2 and 2 flexibly and flexibly React. Then we look up all of these posting lists and intersect them, right? Does that make sense? However, you're going to end up with false positives. Why? Because in that case, you might have this document here that is returned because it has all of them, help ETH, ETH Zurich, Zurich 2, 2 flexibly, flexibly React. Does it contain that sentence? It doesn't. That's a false positive. You see, we are outputting too many results. That would result in a not optimal evaluation matrix, right? Here we have that would be the precision that would be affected because we are returning documents that do not actually contain the sentence. How can you improve that? Well, you can increase the number of words. You can do it with 3, with 4, right? But of course, the problem is that it doesn't scale because now if you compute the size of the index, the more words you add, the higher the number of posting lists. So this is very hard to actually make it scale efficiently, right? So the number of posting lists would every time be like the square, the cube, and so on. So it just doesn't scale. That's the reason why you have another way of doing that, even though you could argue maybe the false positive are okay if you have 4 word indices, for example, but there's another way. What do I want to, oh yes, here I want to show that now it's a true negative. If you do it with 3 by 3, now this document will no longer be returned, right? So we solved this false positive, but you might have other false positives that are trickier, just a bit less of them. Okay. Oh, I forgot I had this slide. So if you do by word indices, 3 word indices, 4 word indices, then this actually increases the number of posting lists in the power of n of the number of terms, right? Okay, so we don't really like that. So let's use a positional index here. What is this? It means that we no longer constrain the model to sets of words. Now we have lists of words. It means that in the postings, I still have the document ID as before. For some reason, I'm using letters here, but don't be just too shocked by that. So C would be the document, probably to disambiguate with the positions. So you have the document ID. Here you have the term frequency. It's not the same as the document frequency you would have here. It's the number of documents. Here it's the number of occurrences of the term in the document. Because in the set of words, we wouldn't know. But we have lists of words. So lists of words, we do know the number of occurrences of each term. So now we know that this term here appears once in document C. We even know at what position. Because in here, I also include a list of the offsets at which the tokens appear, right? So this is called the positional posting. And you might have, for example, here, I have this term 2 that appears in document C 3 times at offset 4, at offset 7, and at offset 11, right? With a positional posting, I can do that. These are called positional tokens because you have the position. Again, very important. This is because we have lists of terms, not sets of terms. This is why we have this. So this is called the positional index. And now, how can we tell that document C contains ETH Zurich? Well, we know that document C contains ETH at position 2 and it contains Zurich at position 3. So 2 plus 1 equals 3, right? So we know that ETH is next to Zurich. There you go. Now we know that ETH Zurich is there. And we know it's not a false positive. Here we know for sure because we have this information. This is it for today. This is chapter 2 of the information retrieval book. Make sure to read it, the term vocabulary and postings this. It also contains many explanations on languages, even more languages than what I did today. So it's a bit orthogonal, but you'll find many other examples in there. So I encourage you to read it. Thank you very much for coming. Enjoy the exercises tonight. If you have any questions about the lecture, ask offline. If you cannot access the Element chat, please tell us. We will add you. Normally, we invited all of you who connected there. Just make sure to connect to elementinf.ethg.ch once, and then send us an email so that we can add you. All right. Thank you very much, everybody, and enjoy your early lunch, and see you at the exercise session tonight. Thank you very much.